Good morning. Today is October 2nd, and we are continuing to wend our way through Chapter 4, where we talk about pure bending. Last time we had gotten pretty much to this point where we were talking about the geometry of pure bending. And now, I want to widen this out a little bit. Nope. That's all I got. Hang on a second. This is tipped. That's what's wrong. Okay, very good. There we are. And so now we're going to talk about how much this shortens. So in other words, if we have a bending moment that looks like this, we're going to have a minus del up here and a plus del down here. And of course, that would be the opposite on the cross section. In other words, if this is a minus del, you're going to have a plus del up here and a minus del down here. All right. So basically, let's do this. I'm not going to go through the entire derivation, but if we consider the original length of this structural member, this prismatic member, to just have some value L, on the neutral axis, since there is no del on the neutral axis, therefore, L equals L. L after the bend equals L before the bend. Okay? And down here we're going to have L prime, which we'll call the length of the bottom, anything below the neutral axis. So that's going to equal L plus del. And up here, L minus del is equal to L prime. Right? So what we're calling this, let's say L prime equals L. So that's just to keep our nomenclature, our symbolism the same. All right. Well, if you look at this, the way that this is bent is a concentric circle. The bend is a circle centered at C, subtending angle theta right here. And that's really interesting because what we can see, just if we keep everything in radians, is if we consider this to be rho is the distance to the neutral axis, L is equal to rho times theta if theta is reported in radians. However, rho and theta are difficult to measure. Those are not things that we can really pick up on just a cursory glance of this. We're not really going to have, and if you think about it also, the bends are usually very, very small, so rho is huge, and so is theta. So you have to go an extreme distance from the structural member to get that, and so it is not a real practical variable. So what we would like to do is to rewrite these equations in terms of things that are easy to measure on the structural member itself. So continuing with that thought, then we can say that L prime, whether it's above or below, is going to equal to rho minus y times theta, where y is the distance above or below the neutral axis. So in other words, all of these represent concentric circles, where this circle is still going to have the same radius. These circles are going to have slightly smaller radii and also slightly smaller lengths. And it's still determined by that angle that is subtended theta. It's negative because above we shorten and below we lengthen. We also know that del, which is the change in length, is going to equal, I guess we could say L minus L prime. I'm going to change that to keep my signs the same. So it's going to be L prime minus L. Yes, sorry about that. Is that better? Yeah. Yes. Okay, we got it now. And finally, if we add these equations together, we find, if we combine these equations, we'll find that del is equal to negative y, or the distance from the neutral axis, times theta. Now, we also know that epsilon, which is the percentage change, or in other words, is equal to del over L, we could define it as minus y theta then over rho theta. And in that way, we can get rid of our thetas, minus y over rho. Right? So this is almost a workable equation. We can always tell where we are on the structural member. Rho is still a little bit squiffier, but we're getting somewhere where we can start to measure some of this geometry. There. All right. So if we then recognize that since the maximum occurs on the top and bottom of the structural member, so in other words, we're doing the most stretching or compressing at the top or the bottom, we can say that epsilon max is equal to C over rho. Or we can say that epsilon x at any distance is going to equal minus yc times epsilon max. All right. So what we're really doing here, we still don't have extremely workable equations. We're going to in a moment. What we've really done is we have confirmed that the change in length is a linear distribution from top to bottom on the structural member, and is 0. So in other words, there's no change of length at the neutral axis. All right. Now, because we are talking about lengthening and shortening, the stress associated with a pure bending moment is a normal stress. Okay? In other words, we're not talking about shear. And that's actually what separates this discussion from a more general type of a bending moment that we'll discuss later on. But in order to, if we have that concentric bending and we have no, well, I'm not even going to say what we don't have. I'll talk about that later. But if we have that kind of a bending that we've induced by doing two couples, equal and opposite couples, and this bend in a concentric circle formation, we don't have any shearing stress. And so it's all normal stress. And there's sort of a corollary of this, that if del is linear across from top to bottom, so is the normal stress sigma. And once again, if we go back to our original picture, we can see that we're going to have a positive sigma down here and a negative sigma down here, because this is in compression, this is in tension, and sigma equals 0 at the neutral axis. So the distribution is the same. Negative sigma max at the top for this type of bending, sigma equals 0 at the neutral axis, and positive sigma max at the bottom. So if we take this same beam and we construct an axis of sigma. We'll have a maximum negative going to 0 at the neutral axis to a maximum positive at the bottom. So both of those are linear distributions from top to bottom, and they are proportional to each other as well. Del is linearly proportional to sigma from the top to the bottom. That's for a prismatic member. We're going to get a little bit more complicated geometry, and we'll have a slightly different distribution at that point. But for a prismatic member, that is the case. All right. So there's a little bit of a derivation on page 244 and 245 that discusses what this sigma looks like mathematically. But basically, let's just do a shortcut here. We'll say since sigma is equal to some sort of a force over an area, sigma times area is equal to a force. And if we take that down to a differential quantity, we can say that we already know that sigma is that linear function. So we can say sigma, if we take the distance we are from the neutral axis to the entire, that would be neutral axis to the top or neutral axis to the bottom, and add a negative sign because we know that on the top, when y is positive, that sigma is negative and opposite. Multiply that by sigma max. Then we have that linear proportion across the cross-section. And if we multiply all of that by dA, because this is sigma right here, so sigma times dA. And if we integrate that, we can say that y and c, well, y is not a constant, but c is a constant, isn't it? And so is sigma max. So we can pull that out. And what we have left in here is an integral of y dA. All right. Now, the other part is that the integral of y dA is the first moment, or q. I'm not going to ask you to remember that from statics at this point necessarily. But if we then continue with this discussion, and we can say that a moment is equal to y times a force. And if we go back here and we think about putting a y here and another y here, we come up with an idea that if a force is equal to negative sigma max over c times the integral of y dA, then if a moment is a y times a force, then we get dm is equal to minus sigma max c times the integral of y squared dA. And you may remember that this integral is called the moment of inertia, which is designated using the letter I. And the meaning of a moment of inertia, primarily moment of inertia is a mathematical concept, but one of the things that a moment of inertia represents is a resistance to bending. So it kind of makes sense that it would come up here. Now, the way that a moment of inertia works is like this. If you have a ruler and you have a shape like this, if this were a bridge, if you lay it out so the span is flat and wide, it's easier to bend it, rather than if you have a bridge like this and it's narrow and tall, it's more difficult to bend. Now the reason is because the height factors in, height to the third usually is what a moment of inertia looks like. So here we have less resistance to bending, and here we have more resistance to bending, even though we have the same size, the same shape, and the same material. So what that's really saying is that the orientation of the material matters as well. So I've done this very briefly because I'm not really sure where you guys are with moments of inertia, and I don't want to spend a lot of time reviewing the concept, but you may want to go back to your statics book. This is covered in chapter 9, and you can see what this looks like. You can learn a little bit more of moments of inertia, but the good news is that moments of inertia are categorized in the back of your book, in your mechanics and materials book. Over here where we have I bars, something I bars, I's, and so forth. So these are all moments of inertia. Now, when we are talking about the types of moments of inertia that we're talking about moment of inertia about the neutral axis, which occurs at the centroid, and we're talking about this in the x direction. So in other words, about an x-axis. So for a rectangle, the moment of inertia about the neutral axis, about a neutral axis in the x direction, is 1/12 times the base times the height third. And for 80% of our material, this is the formula that we're going to use. But it's not always, but it's just like when we did the polar moment of inertia with torque, it was always almost 1/2 times pi r to the 4th. It will almost be this value for us as well. But if we had a different shape, we would have to find the moment of inertia in a different manner. And you may remember that you did using the parallel, do you remember the parallel axis theorem from statics? Yeah, so I don't want to keep a week of your time doing that. So if we come up with a different type of a moment of inertia, I will bring it to your attention. We'll cover it at that time. All right, well, what this means really is that if we take the integral of dm, or moment, that's just m. And so we get that m is equal to negative sigma max over c times I, or mc over I, negative, is equal to sigma max. And since we also know that sigma max and the distance from the neutral axis are proportional to each other, it also follows that sigma at any point is going to equal my over I, where c is the distance from the neutral axis to the top or bottom, and y is the distance from the neutral axis to the point in question. So in other words, y can be anywhere. I'll draw a picture here. Here's my cross-section. Here's my neutral axis. The distance from here to here is c. The distance from here to here is c. And if we're interested in the moment or the sigma at some random point, this would be y, or this would be y. And of course, above the axis, it would be positive. If we're going below the neutral axis, it would be negative, and that's why we have a negative sign out here. Okay. So in terms of sign convention, if your structural member is bent in this shape, that's a positive moment. If it's bent opposite, as you recall, like this, that is a negative moment. Y is positive if you're going up. Y is negative if you're going down. And if you look at I, if it is 1/12 times the base times the height to the third in almost every case, it has dimensions of length to the fourth, and height and base cannot be negative unless it's a cutout of something. But if you have a positive area, this will always be a positive quantity. So it means if you go back here, positive moment, positive y, results in negative sigma, which makes sense because you're looking at compression above that neutral axis, because this is always positive. Positive moment, negative y. Negative, negative is positive. That means you're stretching below the neutral axis. And if you have a structural member that's bent the opposite way, this equation works again, because this would be a negative moment. Positive y results in positive sigma up here. Here we have a negative moment and a negative y. So that would be negative, negative, negative. So that's a negative sigma down here, signifying compression. Okay. Now, these equations, let me rewrite them, or I'll just put them right here. These equations right here are the first set of workable equations that we have that relate sigma to moment across this distribution for a particular moment of inertia on the cross section. And these are referred to as the elastic flexure formulas. Right? And so those are workable working equations for our first set of homework tonight. All right. Now, the other thing is they have a slight abbreviation, and sometimes this value is tabulated. The value of C over I is going to be the same. In other words, every value, every particular cross-section has a given C, and a particular shape will have a given I. So those two together are just referred to as S. It's actually the opposite. It's I over C is equal to S, which is called the section modulus. So if you're using like rolled tubular goods, sometimes the section modulus will be tabulated. All right, so that the equation can be written minus M over S is equal to sigma max. Okay, that's just a direct offshoot of this. It's just because I over C is equal to S. C over I over C, yeah, is equal to S. All right, and then, so I wanted to show you some of the tables in the back of the book again. And as you see, this is Appendix C. This is not one that we would use particularly, but this is a specific type of a rolled steel shape in U.S. customary units. This is called an angle of unequal legs. Okay? If you look at Appendix C, the first page, this is an angle of equal leg. So in other words, these are specific called out nominal shapes. So if one looks like this, for example, it tells you a size. This is in SI units. Let's go back to the English units over here. So if you have an L 8 by 6 by 1 or L 8 by 6 by 3/4, it just means this very specific thing, and it gives you the measurements of X and Y here. But basically, you have a different weight per foot and a different area for each of those. And you have here the first column in the XX axis is I sub X, that's the moment of inertia. The next one is S sub X, which is the section modulus, which is just I over C. And then we just have some other values of R sub X, which is that, and R sub Y, and just Y, which is in inches right here. Right? So there's a lot of different shapes. I-beams are also rolled steel shapes. These angles are all rolled steel shapes. We have like C-shapes, which look like this, but all of them have that same data tabulated for them. We have there's just an I-beam, and so forth. So sometimes we'll construct an I-beam of our own or construct a shape of our own, but other times we'll use something that is a standard shape. And then you can use this data instead of having to compute a moment of inertia or a section modulus. All right. Any questions yet? Well, let's do a quick problem, and then we'll give you a couple homework problems, and we'll be good to go. All right. I'm going to do problem 4.1, and then okay, let's just take a look at that. Let's do problem 4.1. We have a beam that is extruded from a wall, and it is subjected to a moment in the amount of 15 kilonewton meters. All right, now if you think about this beam, if it's subjected to a moment that looks like that, is that a positive moment or a negative moment? It is. Very good. All right. Now it asks us for the stress at point A and at point B. And the cross section, you'll see there's little dashed lines here. And if you've had CAD or drafting, you know that that means there's something going on that's hidden to the axis. So what's hidden is we have a hollowed out prismatic member, and we wish to know the stress here at B and the stress at A. Okay, well, since it's subjected to a moment, we know that sigma is equal to m negative my over I. We know what our moment is. We know at point A what our y is. It's the distance from the neutral axis up to point Y. We're told that this entire span is 80 millimeters. So I'd say 0.80 meters, just because it's easier if you keep everything in base units. So the distance from here to here is 40 or 0.04. Okay, because the neutral axis is halfway in between because of symmetry. And so the only thing we have to find is I. For sigma B, we have minus, same moment, 15 kilonewton meters. But now point B is all the way down, so it's a negative value. The whole thing is 80 plus 20 plus 20, which is 120, or it would be 60 from here to here, or 0.06. And because it's below the neutral axis, it's a negative. And so once again, we are confronted with finding I. I will be the same in both cases because I is about the neutral axis. Well, if this were a rectangle, it would be 1/12 times the base times the height to the third. Okay, but we have a positive area, which is the larger area, and then we have a negative area, or the cutout of this rectangle in between. Now, since this is symmetrical, everything works about the same neutral axis, so that's a good news. We can factor out the 1/12. For the outer rectangle, we have the base is 40 plus 20 plus 20, which is 80 millimeters, or 0.08 meters, times the height, which is 120, or 0.12 meters to the third power, minus what's going on the inner rectangle, which is 40 millimeters or 0.04 meters, times the height of the inner rectangle, which is 0.08 meters raised to the third power. And so you'll notice that my I value is 1/12 times some quantity, but we have meters to the third times meters, which is meters to the fourth. And that's a good unit for a moment of inertia. All right, so doing the math here, let's start with this. And if we take 0.12 and multiply it by itself 3 times, and multiply that by 0.08, this first quantity turns out to be 0.0001384, and this quantity 0.08 times 0.04. This turns out to be 0.00002048. Okay, so the quantity in the brackets is 0.000111776. And when we take that number and we divide it by 12 to get our final answer, we get a wee little number of 9.813 repetent 3 times 10 to the minus 6 meters to the fourth. Okay? So that means all we really need to do is to put that here. And the first thing we need to do is to decide what our units look like. We have meters squared on the top, which cancels this to meters. If we cancel meters squared against meters to the fourth, we have meters squared on the bottom. We have kilonewtons per meter squared, which is a kPa, and that is a good unit for sigma. We have a negative value, which if we look at it, that is going to be a negative value because it's in compression. And so if I do the math, then take this 15 kilonewtons and this 0.06, I get a value of 91711 kPa, which is minus 91.7 MPa. Okay, so that's the value of the stress right here. Okay, so if we do the same thing here, here we have a negative times a negative, so this becomes a positive. We have the same 15, but now we have 0.6. We have the same moment of inertia. So we have 15. Hang on, I got to clear this because I'm using a bad little calculator. 15 times 0.06 divided by 9.813. And so I get that number times 10 to the 6th. I get, that doesn't seem right. I did something incorrectly here. I think I pulled the wrong value here, didn't I? Let me do this again, because I got the same value again. So I think what I did was, I think I didn't use 0.4. I think I accidentally put in 0.6 here. I'm trying again, 15 times 0.04 divided by 9.813. Yeah, this value is, I accidentally just picked up this. This is actually right here. And this value is negative 61.1 MPa. All right. So do you have any questions about that? Like I said, you may have to go back, depending on where you are with moments of inertia, you may have to go back to your statics book and review that a little bit, but we're not going to ever go to the integral form. We're just going to do it. If you need to review something, review the parallel axis theorem, and we'll do that. But mostly, just remember, we're always taking the moment of inertia about the neutral axis, which is at the centroid of the cross-section by definition. And so if we have symmetry, we can just use that and fold it in half. If we don't, if we had a T-shape or maybe an I-beam where the top was thicker than the bottom, like the top web or flange was thicker than the bottom, we would have to do a little bit of manipulating, but we can always use the parallel axis, so we won't go to the integral form. Okay? I hope that's kind of familiar, but we'll see. So what I would like you to do then, for your homework, do problem 4.2. And like something with a little more symmetry. Okay, they really get into the non-symmetric things really quickly. So also do 4.9, but please start 4.9, and if you have trouble with the moment of inertia, let's work on that when we come back to class on Wednesday. All right, that's it for today, gentlemen. Stop.